This is A. Srinivas, Lecturer in Physics, Vignan Junior College. Students, welcome to Vignan online classes. So in this part of our discussion, in this session, I would like to explain some important equations which are very much useful in all objective types of exams, that is JEE Main or EAP set or JEE Advanced. For any competitive exam, to attempt objective questions effectively, especially in charge and field chapter, I would like to revise very important equations belongs to dipole as well as the gausslaw and its applications. So let us have a look belongs to them. So this is objective formula revision especially. So belongs to charge and field chapter. In charge and field chapter, in this session, I selected two important topics. One is electric dipole. Second one is Gauss law and its applications. So Gauss law is the very important in JEE Main examinations, especially when you go through the previous JEE Main and advanced examinations. Most of the questions from electrostatics chapter belongs to this Gauss law and these applications. So electric dipole and Gauss law and its application. In these two topics of charge and field, I revise all the equations. So let us start these equations. First of all, what is meant by electric dipole? Two equal in magnitude, opposite in direction charges kept at some distance of separation constitute a dipole. Here, let us look into it. So here you have a dipole. So let us see. So electric dipole means if we have two equal unlike charges, at this point let minus q be the charge at one point. So we have another charge plus q. These two are at some distance of separation and separated by some 2L or something. 2L is the distance of separation. This constitutes a dipole. Then first very important parameter is dipole moment. Dipole moment is a vector quantity and magnitude of dipole moment is q into 2L, product of charge and length of the dipole, and direction of dipole moment is directed from negative to positive charge. This is the direction. Negative to positive charge is the direction of dipole moment. Unit vector along this negative to positive direction is I cap. Then dipole moment is the product of charge and length of the magnet, and it is directed from negative to positive charge. For any further discussion of dipole, we apply dipole moment and its direction as explained here. So next come to the electric field intensity due to electric dipole. So here this is electric field intensity due to electric dipole. Here at a point on the axial line. So here let us first discuss what is the electric field intensity due to electric dipole on its axial line. We know that line joining the negative and positive charge is electric dipole. Then what is the electric field intensity along the axial line of electric dipole? Let us consider that minus q be the charge of the electric dipole at one point and plus q is the another charge. These two contribute to electric dipole whose dipole moment is directed from negative to positive charge. Here the line joining AB is the dipole axis and O is the midpoint of the dipole. Here length of the dipole is 2L, so that A at a distance L and as well as B at a distance L from O. Then dipole moment, let us consider one arbitrary point P on the axis of the dipole. We would like to know the electric field intensity at a point on the axial line. At point P is arbitrary point on the axial line of the dipole. We have to write the expression for electric field intensity at that point. Here for that we calculate this one and ultimately we get the electric field intensity. Here let us look into it. This is the ultimate formula. as we are revising, here I strictly confined to the final expression. That is my aim. Here, when you consider point P on the axial line, at a distance x from center of the dipole, then electric field at that point, ultimately we get 1 by 4 pi epsilon naught into 2p into x by x square minus L square whole square. Here x is the distance of the arbitrary point P from center of the dipole, and P is the dipole moment that is directed from negative to positive charge. 2L is the length of the dipole. In such scenario, electric field due to the given dipole on axial line is given by 1 by 4 pi epsilon naught 2px by x square minus L square whole square, and it is directed along the direction of, it is along P cap. So it is along P cap. Along the direction of dipole moment, we have the net electric field of the dipole. So here this I cap shows the direction of dipole moment. When L is very less than x, for practically considering dipole, if you consider dipoles in molecules, then dipole length is very small value in the dipoles of molecules. L is very less. X is the distance at which we are finding the electric field due to the dipole at outside point. In such situations, L is very less than x. L is the length, half of the length of the dipole is very less than the x value at which we are finding the electric field. Then x square minus L square is approximately equal to x square whole square. Therefore, x square whole square means x power 4. X by x power 4 means x cube. So, in most of the problems, we prefer this equation. That is electric field due to dipole of dipole moment P at a distance x from center of the dipole on its axial line is 1 by 4 pi epsilon naught 2p by x cube along dipole moment direction. This is the ultimate formula. Remember it. Here direction is along the direction of dipole moment. Okay, next we would like to consider another case. This is the case. We would like to find the dipole, the electric field due to dipole on an equatorial line. At equatorial line, at a point on equatorial line, we would like to find, let us describe the dipole. So, minus q is the one charge of the dipole at A, plus q is another charge of the dipole at B. Then O is the center of the dipole, P cap is the dipole moment directed from negative to positive charge, P cap. As usual, 2L is the length of the dipole. So let us have a line, equatorial line. Here any line perpendicular to dipole length and passing through the center. Line perpendicular to the dipole length and passing through the center is equatorial line. Let Q be one arbitrary point on the equatorial line of the dipole. We would like to know the expression for electric field at this point, at the equatorial line. So, we do the derivation and ultimately we get the expression for electric field intensity on the dipole. So, after having this derivation, I would like to give a final expression for it. So this is the expression, students. Due to this dipole, at equatorial, a point on the equatorial line, which is at a distance x from center of the dipole, let us consider this one as x from center of the dipole. The electric field at point Q is at a point on the equatorial line at a distance x from center of the dipole is 1 by 4 pi epsilon naught q into 2L by x square plus L square whole power 3 by 2. Q into 2L is dipole moment. Hence, this is the expression 1 by 4 pi epsilon naught p by x square plus L square whole power 3 by 2. 1 by 4 pi epsilon naught p by x square plus L square whole power 3 by 2. When you compare the direction of resultant electric field, this arrow mark is opposite to the direction of P bar, dipole moment. So on a point, on equatorial line, electric field due to dipole is opposite in direction to the dipole moment. So the unit vector is minus P cap, opposite to the direction of dipole moment. So observe the expression here, 1 by 4 pi epsilon naught P by x square plus L square whole power 3 by 2 minus I cap, where I cap is the dipole moment, minus I cap is the opposite direction to the dipole moment. So as usual, if L is very less than x, so L means half of the dipole length, x is the distance at which you are finding the electric field. If L is very less than x, then x square plus L square is equal to x square whole power 3 by 2 means x cube. So 1 by 4 pi epsilon naught, ultimately this is the expression, 1 by 4 pi epsilon naught P by x cube. So this is, once again I am writing here, P by 4 pi epsilon naught, 1 by 4 pi epsilon naught x cube is the equatorial value. So electric field at a point on equatorial line is given by that expression opposite to the direction of dipole moment. So if we consider a dipole having minus q and plus q, suppose let P be a point on axial line at a distance x, then electric field at point P is given by 1 by 4 pi epsilon naught 2p by x cube along the p cap direction, whereas at the same distance x on equatorial line, net electric field at point Q is along this direction EQ. Here that EQ is given by this formula, P by 4 pi epsilon naught x cube. Then for the same distances consider, if same distances are considered an axial line and equatorial line, here on axial line we get double the value of equatorial line. On axial line in the expression we have 2, so electric field on axial line is double that of equatorial value when those 2 points are considered at same distance. One is an axial line, another one is equatorial line at same distance. Then on equatorial line electric field is double the electric field on axial line, electric field is double that value on equatorial line. Students, next consider the another one more expression, that is torque on electric dipole in uniform electric field. Torque on electric dipole in uniform electric field. So let us consider electric dipole as shown in the diagram here. The dipole is extended from minus q to plus q, length of the dipole is 2l, and it makes theta angle with direction of electric field. So it is making theta angle with direction of electric field. Dipole moment is directed from minus to positive charge. Here this is the direction of electric field. On positive charge, force exerted by the electric field is QE in the direction of electric field. On the negative charge it is QE opposite to the direction of electric field. So these are the forces, and these two forces constitute a couple, and this couple produces torque on the dipole. So the torque on the dipole is force into perpendicular distance. So in the couple the magnitude of force is QE, and perpendicular distance, this value is equal to 2l sin theta. So that here we replace Q into 2l by dipole moment P. Then expression for torque acting on the dipole, tau, let us tau be the term that gives the torque, that value is equal to P sin theta. In vector form, tau bar is equal to P bar cross E bar. In vector form, that is P bar cross E bar. So here this is the main expression. In magnitude form P sin theta, in vector form P bar cross E bar. Here we consider some cases of this formula. Case 1, if suppose this dipole is kept along the direction of electric field, dipole is kept along the direction of electric field, theta is equal to 0 degrees, P bar and E bar are parallel to each other, theta is 0 degrees, use theta 0, torque is 0, tau is equal to 0. If theta is 90, dipole is kept like this along y direction, whereas E bar is along x direction, then theta is 90, then tau is equal to Pe sin 90, that is equal to Pe. When dipole movement is perpendicular to the electric field, there is maximum torque contribution Pe. When dipole is parallel, then torque exerted by the electric field on the dipole is 0. Here, next we would like to find out work done on electric dipole in uniform electric field. So let us consider a dipole having negative and positive charges. They are shown here, negative and positive charges, and length of the dipole is 2L. Electric field is a uniform electric field is there, in which we kept a dipole E bar. Initially, the dipole is making theta 1 angle with the direction of E bar. This is E bar direction. With the direction of E bar, dipole is making theta 1 angle. Now, to rotate the dipole, so let us look it. Initially it is making theta 1 angle. Let us see the animation in which we are rotating the dipole to another angle theta 2. So, if you displaces, before displacing to theta 2 angle, for very small displacement d theta from its original angle theta 1 to rotate the dipole by very small angle d theta, let us write the expression for work. So here the work done to rotate the dipole through very small angle is W is equal to tau into d theta. Then total work done, that is tau is Pe sin theta d theta. We know that torque is Pe sin theta. Then for small angle of rotation, work done is given by P sin theta d theta. To have total work, let us integrate. Let us assume dipole is rotated from initial angle theta 1 to the final angle theta 2. For this total rotation of the dipole in the given electric field, work done is integral P sin theta d theta from angle theta 1 to theta 2. Here we know that integral sin theta, here this is equal to P into minus cos theta. Integration of sin theta d theta is minus cos theta. The theta value changes from theta is equal to theta 1 to theta is equal to theta 2. Now it is minus of cos theta 2 minus cos theta 1. Take minus into the bracket, we get P of cos theta 1 minus cos theta 2. So this is the required expression, students. If any dipole initially kept at theta 1 angle in the given electric field, P is the dipole moment, E is the strength of electric field, of uniform electric field. If the dipole is rotated from theta 1 angle to theta 2 angle, then work done for that rotation is P of cos theta 1 minus cos theta 2. Here, to have the potential energy of dipole at any arbitrary point, arbitrary angle, to have potential energy of dipole in given uniform electric field at some arbitrary angle theta, initially we have to consider 0 work point, that is when dipole is at 90 degrees, cos 90 is 0, so potential energy is considered to be 0 at 90 degrees angle. When the dipole is rotated from 90 to theta, we consider 90 because at 90 cos 90 is 0, work done is 0, so we are considering from 0 work. Let us consider theta 1 is 0 and finally it is rotated to an angle theta 2 is equal to theta. From theta 1 is equal to 90 degrees angle. Then substituting these conditions in the above formula, theta 1 90, cos 90 0, theta 2 theta, so minus Pe cos theta. This is the one more important expression of the dipole in uniform electric field. Potential energy of given dipole in uniform electric field is minus Pe cos theta. Here, if theta is 0, then potential energy, if dipole is at particular angle 0 degrees, that is dipole is kept parallel to E bar, then potential energy is minus Pe. This is known as the stable equilibrium position. when theta is equal to 0. Because the potential energy is least, minus PE. Minus PE means lowest value of potential energy. Hence it is a stable equilibrium. At theta 90 potential energy is 0 and at 180 potential energy is maximum plus PE. So maximum. So this is said to be unstable equilibrium. At theta 0 torque is 0 as well as at theta 180 torque is 0 because torque is equal to PE sin theta. So for 0 degrees as well as 180 degrees torque is 0. Torque 0 means we can consider the condition as the equilibrium, but with minimum potential energy at 0 degrees angle, torque 0 and potential energy is least value, hence it is stable equilibrium. At theta 180, torque 0 as well as potential energy has greatest value, it is unstable equilibrium. Remember, sometimes in JEE main, the questions were given. What is the work required to rotate the dipole from stable equilibrium to unstable equilibrium? Indirectly, it is rotated from theta is equal to 0 degrees to theta is equal to 180 degrees. That is the rotation from stable equilibrium to unstable equilibrium. Here, next one. Here we are considering area vector. If you consider any area, the area is a vector quantity which is directed from normal to the surface. If this is the surface, any line drawn normal to the surface shows the area vector. Here ds bar is the area vector, ds is its area. Suppose if we consider this area bounded here, that is ds, then area vector is a vector perpendicular to the plane. ds into n cap is area vector. So electric flux, total number of electric lines of forces passing through given area. Here some area is given. When you look into the diagram, some arbitrary area is there through which some number of electric lines of forces are passing. Total number of electric lines of forces passing through given area is known as the electric flux, denoted by pi. Electric flux is denoted by pi. And here let us consider the d pi. So the electric flux through very small area is given by E bar dot ds bar. Suppose if you consider small area here, I selected some part of the area of the given shape and ds bar is directed like this. This is the area element whose area is ds and its area vector is ds bar as shown here, and the electric field is like this, E bar. Then angle between E bar and ds bar is theta. Then flux passing through this area, this confined area, is d pi is equal to E bar dot ds bar. And if you expand the dot product formula, EDS cos theta, then total flux through the given arbitrary shape, this is the given arbitrary shape, total electric flux through the given arbitrary shape is integration of this formula, that is pi is equal to integral E bar dot ds bar. Integral E bar dot ds bar is the total electric flux through it. So in that way, this is the very important expression to find the flux. We apply repeatedly this formula in the applications of Gauss law. So here let us comes to the very important topic, applications of Gauss theorem. Electric field intensity due to infinite long straight charged wire. The first case is electric field intensity due to long straight wire. Infinite, this is infinite long straight charged wire. Due to this infinite long charged wire, we have to find the electric field intensity. So once again, students, let us look into the diagram. In this animation we are finding this is infinitely long uniformly charged wire. This is the infinitely long uniformly charged wire. Due to this charged long wire, we have to find the electric field around it at some arbitrary distance r. So let us have the diagram. So here, to find the electric field due to this wire at a distance r from the charged wire, let us assume a Gaussian surface. This green shaded part in the animated diagram shows a Gaussian surface in form of a cylinder of radius r, and here length of the cylinder is L, and we have three areas in it. So here we have three areas. This is the flatted area for which E bar and ds bar are perpendicular. For this flatted area also E bar and ds bar are perpendicular. For curved area of the Gaussian surface, E bar and ds bar are parallel. So Gauss law, integral E bar dot ds bar is equal to q by epsilon naught. Total electric flux passing through any closed surface is 1 by epsilon naught times the total charge enclosed by the surface. By using that formula, we ultimately get, as the flux through the flatted surface cancels, only flux through the curved surface is present. Therefore, integral EDS is equal to sum of the flux through the three surfaces. And here, integral EDS is E into 2 pi RL. Here, ultimately, the expression is integral EDS is E into 2 pi RL, integral EDS, Q by epsilon naught, as L is the length of the cylinder, lambda is the charge per unit length, then Q is equal to lambda L. Charge per unit length is L, charge per unit length is lambda, length of the cylinder is L, then charge enclosed by the cylinder is charge per unit length into L, Q becomes lambda L by epsilon naught. On cross multiplying, we get E is equal to lambda by 2 pi epsilon naught R. This is the required expression. Electric field due to very long uniformly charged wire having linear charge density, charge per unit length lambda. So as already we observed, if you have a charged wire like this having uniform charge density lambda, a distance r from it, the electric field is given by this formula, lambda by 2 pi epsilon naught r. Here, when you multiply with 2 in numerator and denominator, it becomes 2 lambda by 4 pi epsilon naught r. We know that 1 by 4 pi epsilon naught is 9 into 10 power 9. So according to it, we get this formula. So, and it is directed along the direction of r cap. Electric field is radially outward from this infinite long wire. So remember this formula. This is the very important formula, belongs to electric field due to charged wire. So let us consider one more case. Electric field intensity due to an infinitely long thin plane sheet of charge. We have this is also infinitely distributed. A plane sheet, a long thin plane sheet in which charge is distributed uniformly, and we consider infinite plane sheet having a uniformly charged distribution with surface charge density, that is charge per unit area. Surface charge density or charge per unit area is sigma. So sigma shows the surface charge density of the plane sheet, and to find it we consider a Gaussian surface in form of a cylinder passing through the infinite plate like this. And here let us consider the cylinder of length L and radius r. Cylinder is a Gaussian surface passing through it of length and radius r. Here also the electric field is directed like this towards right side, and towards left side electric field is directed like this. So for this right side flatted area, E bar and area vector are parallel. For left side flatted area, E bar and area vector are parallel. For curved surface, the E bar and area vector are perpendicular. If you consider the curved surface, so curved surface area vector is like this, E bar is like this, perpendicular. So for flatted area, it contributes the flux because E and ds are parallel, this circular flatted areas. For curved surface, it contributes no flux because the angle is 0. Once again we are considering Gauss law, that Gauss law is here integral E bar dot ds bar is equal to q by epsilon naught. Integral E bar dot ds bar is contributed by the two circular flat areas on either side. So Q is contributed by the charge enclosed by the surface. So charge present in this area S, charge present in this area is the charge of this formula. By substituting the left hand side equations and right hand side equations in the above formula, and ultimately we get the total area E into S on one side, E into S on another side. So integral E bar dot ds bar is equal to E into 2E into ds, or that's also equal to, let it be 2Es. S is the area of each circular plane. S is the area of each circular plane. Of course, that is equal to pi r square. Then 2Es is the flux passing through Gaussian surface. Then Q by epsilon naught. So in the given plane sheet, Gaussian surface is passing through r radius. So charge contributed by circular area is charge density into area. So sigma into pi r square by epsilon naught. So that by equating LHS and RHS in the Gauss formula, so integral E bar dot ds bar is 2E into S. S is pi r square. Q by epsilon naught. Charge enclosed by the plane sheet through Gaussian surface is charge density into area pi r square. On both sides the pi r square get cancelled. Then we get the expression for E is sigma by 2 epsilon naught. Ultimately we get E is equal to sigma divided by 2 epsilon naught is the expression for the electric field intensity passing through it. So for infinitely plane sheet of charge having surface charge density sigma, then electric field intensity at the beside of the plane sheet at any distance, which is independent of distance, sigma by 2 epsilon naught. So here this is the expression. If the plane sheet is thick, consider this special case. If plane sheet is thick, then the not thin, so far we consider thin sheet. If it is thick, then the charge is distributed will be available on both sides. If you consider a thick plane sheet instead of thin plane sheet, so let us have a thick plane sheet. Then there are charges at either side, as I am showing, and either side of the plane sheet there is a charges. Then the charge is 2 sigma into S. 2 sigma into S or sigma into 2S on both sides of the plane sheet. Here on either side of the plane sheet there exists charge. So total charge contributed by the Gaussian surface is sigma into 2S. So in this place we get sigma into 2 pi r square. Therefore 2 get cancelled. For that thick sheet we get E is equal to sigma by epsilon naught. Generally we have the main derivation for thin sheet, that is sigma by, don't get confused, sigma by 2 epsilon naught. Okay, this is the case. We go to the next case. Electric field intensity due to the two parallel infinitely long thin plane sheets of charge. So far we discussed about one thin sheet and one thick sheet, but here I am highlighting the points. Electric field due to two parallel infinitely long thin plane sheet of charge. This topic was given number of times in JEE main examination. There were problems given already and this is a repeatedly given topic. So let us consider, in spite of one, if we have two uniformly charge distributed infinitely long thin plane sheets, then what is the electric field due to them? So let us consider the case 1, in which we have two plane sheets. One plane sheet of charge density sigma 1 and another plane sheet in blue color as well as in yellow color. We have two thin plane infinitely uniformly charge distributed sheets. On first sheet the charge density is sigma 1. Second sheet charge density is sigma 2. They are kept as shown in the diagram such that we assume one condition, sigma 1 is greater than sigma 2. Now the electric field at different regions. So I would like to know the electric field in region 1. Region 1 is left side of the both the plates. Left side of the both the plates is region 1, in which electric field due to first plate is away from the first plate towards left side, and due to second plate also electric field in this region is away from positive plate. Electric field due to positive plate is away from positive plate. So if you consider this region, here I am indicating it at this region, which is left of the both the sheets, then electric fields due to first and second sheets are leftward direction. So these two added up, then E bar is sum of E1 and E2. So in region 2, your electric field in this region, and in this region 2, due to sigma 1 it is directed rightward, due to sigma 2 it is directed leftward. These two are in opposite direction. As sigma 1 greater than sigma 2, E1 greater than E2, both are in opposite direction. We have to take E1 minus E2 in region 2. If you consider region 3, right side, both are added up. Both are in the same direction. So by knowing it, as we explained very clearly, in region 1, both the electric fields are towards left. Then net 1 is E1 plus E2. We know that E is equal to sigma by 2 epsilon naught. Hence we get E1 plus E2, sigma 1 by 2 epsilon naught plus sigma 2 by 2 epsilon naught. It becomes sigma 1 plus sigma 2 by 2 epsilon naught. For region 2, these two are in opposite direction. Hence E1 minus E2, sigma 1 minus sigma 2 by 2 epsilon naught. In region 3, at right hand side of the both the plates, then these two are also in same right hand side direction. They are added up, E1 plus E2, so that we get sigma 1 plus sigma 2 by 2 epsilon naught. This is a special case, which is one extension to the thin plane infinitely uniformly charge distributed sheet. Here, for the same scenario, if the charges are opposite, here, then what is the situation? So we get it now, we calculated it. So it comes to the next case. Electric field intensity due to a uniform charged thin spherical shell. Electric field due to spherical shell. So let us consider a spherical shell. So look into the diagram, here see the animation. This is the spherical shell. O is the center of the shell and R is the radius of the shell. This is hollow, there is no charge, only charge is present on the surface of the shell as shown in the diagram. Here, let P be any point at outside, let Q be the charge present on the surface of the sphere and it is distributed uniformly. Here already it is written as small q. P is any point, let the distance of P is smaller, which is arbitrary point. So to find the electric field at that point, we consider a Gaussian surface, a closed sphere at radius smaller around the given charge, and by using Gauss law we calculate the, so integral E bar dot ds bar is equal to q by epsilon naught is the equation. Every time we use the same expression. Integral E bar dot ds bar is E into 4 pi r square. 4 pi r square is the area. E into 4 pi r square is equal to q by epsilon naught. So ultimately we get E is equal to, remember this formula, at outside point of uniformly charged distributed shell at any distance small r greater than capital R at outside point, the electric field is 1 by 4 pi epsilon naught q by r square, and it is exactly equal to electric field due to point charge formula. So comes to surface. On the surface, small r is equal to, here before knowing it, of course the Q is equal to surface charge density into area. Q is equal to surface charge density into area. So replace denominator, numerator by sigma into 4 pi r square. 4 pi get cancelled. Of course, at same outside point, in terms of surface charge density, sigma by epsilon naught into capital R by small r whole square. Sigma by epsilon naught into capital R by small r whole square in terms of surface charge density. Next, come to the surface. When you comes to the surface, here in the above formula small r becomes capital R. So 1 by 4 pi epsilon naught q by small r becomes 1 by 4 pi epsilon naught q by capital R square on the surface. 1 by 4 pi epsilon naught q by r square on the surface, and q is equal to surface charge density into area, sigma into 4 pi r square, then capital R square and 4 pi get cancelled, and finally the expression is sigma by epsilon naught on the surface, sigma by epsilon naught, outside sigma by epsilon naught into capital R by small r whole square. Here I would like to write electric field intensity, ultimately, finally, electric field intensity due to dipole at some arbitrary point which makes theta angle. So let minus q be the charge of the dipole at one end, at the other end the charge of the dipole is plus q, O is the midpoint of the dipole, 2L is the length of the dipole. Let P be any arbitrary point in the space around the dipole. The line joining O and P, so OP, line joining O and P makes theta angle here. For this arbitrary point P, for which the line joining makes theta angle, we find the electric field due to the dipole at this point. The expression at E at the point P is given by 1 by 4 pi epsilon naught into P divided by, if distance is R, P by R cube into square root of 1 by 4 pi epsilon naught P by R cube. We get one different term here, 1 plus 3 cos square theta. 1 plus 3 cos square theta. Here the direction, actually this is the direction, axial line direction. So once again let us see the derivation, what so far I explained. So for the given dipole having charges minus q and plus q, once again I am writing it at theta angle for arbitrary point P. We get the electric field maybe resultantly along this direction E bar, ultimately making theta angle with this OP line. Then that E we get 1 by 4 pi epsilon naught P by R cube into square root of 1 plus 3 cos square theta. That's what I explained. And the angle made with the initial direction is alpha, such that tan alpha is equal to half tan theta. Tan alpha is half tan theta. The direction of net electric field at this point makes alpha angle with OP line, and alpha is given by half tan theta. Of course, the angle with dipole axis is theta plus alpha. By knowing alpha, theta plus alpha is the angle made with dipole axis. On axial line, when you consider the subcases, an axial line, if you consider theta, theta is equal to 0 degrees. If you consider P on axial line, this theta reduces to 0. Cos 0 is 1, root of 4 is 2. Hence formula becomes, on axial line, the formula becomes 1 by 4 pi epsilon naught 2p by r cube. On equatorial line, second case, on equatorial line, theta is equal to 90 degrees. If you consider any point on equatorial line, it makes 90 degrees angle with dipole axis. Then E on equatorial line is equal to 1 by 4 pi epsilon naught p by r cube. So these two are the actually subcases of this main formula. For a spherical shell, When small r greater than capital R, which is outside point, the electric field is 1 by 4 pi epsilon naught q by small r square. When small r is equal to capital R, then E is equal to 1 by 4 pi epsilon naught q by capital R square. Next, at inside point, if you consider inside point of the spherical shell, so let me show the diagram. Here inside point means here. Case 3, at any inside point. If you consider the Gaussian surface at any inside point, no charge is there, Q is equal to 0. So E integral ds here E integral ds is equal to Q by epsilon naught, which is equal to 0. This implies E is equal to 0. For any inside point, E is equal to 0. These are the conclusions. At outside point, 1 by 4 pi epsilon naught q by small r square. At inside point, 0. On the surface, q by r square. And when you plot the graph for this situation, by taking electric field intensity along y-axis and the distance measured along x-axis, for small r is equal to 0, from small r is equal to 0 to r is equal to r, between these 2 points electric field is 0. At r is equal to r, there is a maximum value, and for small r greater than capital R, E proportional to 1 by r square. For small r greater than capital R, so graph is like this. When small r greater than capital R, it is inversely proportional to r square. So up to surface, from center up to surface, there is no electric field. Y coordinate is 0, and it starts at the surface, and beyond the earth surface, beyond the surface of the shell, at outside point, the relation is here in this region E 0. Beyond the spherical shell, E proportional to 1 by r square. This is for hollow spherical shell. And let us find the electric field intensity due to uniformly charge distributed solid sphere. For this also, for outside point, electric field is 1 by 4 pi epsilon naught q by r square at outside point. On the surface, 1 by 4 pi epsilon naught q by r square, small r is equal to capital R. These two cases same as the hollow sphere. For even for uniformly charge distributed solid sphere. So charge is there uniformly, it is distributed inside the sphere also. For that, at outside point, formula is 1 by 4 pi epsilon naught q by small r square. On the surface, 1 by 4 pi epsilon naught q by capital R square. And at inside point, when small r less than capital R, at inside point, when you apply E integral ds is equal to q inside by epsilon naught Gauss law. So E into integral ds is 4 pi r square is equal to 1 by epsilon naught into q inside is equal to volume into charge density. So charge density into volume of the Gaussian surface. Charge density into volume equal to charge. So E into 4 pi small r square is equal to 1 by epsilon naught into rho. Rho means charge per unit volume. That is Q by, let Q be the total charge, by volume means 4/3 pi r cube into volume means 4/3 pi small r cube, volume of the Gaussian surface. So 4/3 pi get cancelled in numerator and denominator, then E is equal to 1 by 4 pi epsilon naught into Q into here r square r cube means r is the remaining value, r by r cube. 1 by 4 pi epsilon naught q into small r by capital R cube. This implies we conclude that E proportional to small r. If a graph is plotted for this situation by taking E along y-axis and small r distance from center along x-axis, from r is equal to 0 to r is equal to capital R, the E proportional to small r. So we get E proportional to small r. We are using this final condition. Inside the solid sphere, from center to the surface, E proportional to small r. On the surface, this is the value. Beyond the surface, E proportional to 1 by r square. E proportional to 1 by r square. So this is for electric field due to charge distributed solid sphere. Here, students, in this part of our discussion, especially my intention is to explain a quick revision of JEE main formulas, which are very much essential for any objective examinations, especially charge and field chapter. I revised the two important topics. One is dipole, electric field due to dipole, torque acting on the dipole, work done in rotation of dipole, as well as gausslaw applications such as electric field due to linear charge density, uniformly charge distributed plate, spherical shell, and uniformly charge distributed solid sphere. For different cases, we derived the expression for electric field. Student, I hope you followed my class, you understand the expressions. Please revise them, and they are very much helpful to you. Thank you very much.